Our next speaker is Galyna Livshyts. She's an assistant professor at the Georgia Institute of Technology and currently a research fellow in the probability program. Galyna will be using a scribble board to give us a talk. Galyna.
Thank you very much. So let me actually put the scribble board in the chat. In fact, I think that my connection is not working so well. I'm very happy that I've opted to that scribble board option. I'll be scrolling it. So you can follow also the link in the chat to follow the slides, this very short presentation. I'll talk about the smallest singular value of inhomogeneous random matrices. So imagine that somebody asks you the following question. Pick a large integer, perhaps 1,000,000, and say somebody gives you a fair die and asks you to flip it n square times, so 1,000,000 square times. You get a bunch of outcomes from 1 to 6, and you can fill an n by n matrix with these outcomes. So it's a random matrix of size n by n. Question, how likely is this matrix to be invertible? Next, imagine somebody asks you a slightly more difficult question. Instead of one fair die, suppose you have a whole bunch of maybe 1,000,000 squared different dice. And some of them may be cubic, some of them octagonal, some of them simplicial. And instead of rolling the same die, every time you need to fill an entry of this matrix, you roll a different die. And fill your matrix with the outcomes. And again, the question is, how likely is this matrix to be invertible? So surprisingly, so while the first question has been studied quite a lot, the second question has not been studied that much. In my recent work with Tikhomirov and Vyshenin, we showed that under very general assumptions, one can prove the optimal, essentially optimal estimate on the smallest singular value of a random matrix with these different entries. So imagine you have a random matrix with independent entries. On average, the Hilbert-Schmidt norm of this matrix is bounded by something of order n squared. And suppose also there is an auxiliary assumption that the entries are uniformly anti-concentrated, meaning that basically they're not all equal to the same number with high probability. They are truly random. So assume that, yeah, they're truly random, roughly speaking, uniformly. Then the smallest singular value with very high, overwhelmingly high probability is bigger than something over square root of n, where again n is the size of the matrix. And this property, this behavior is optimal in a way. Let me also mention another result of earlier result of mine. By the way, sorry, I need to probably say a few words about history. So there's been a huge history in this regard with important results obtained by Shabik, Spielman, and Teng, and Wilson, and Vyshenin, and Tao, and Wu, and Vibrova, and Tikhomirov, and Litvak, and Tomchak, Jagerman, and Pajor, and many, many others. And pretty much with the same set of names, many, many things were known also before about this question. So suppose instead of considering a square matrix, we consider a rectangular matrix with, again, independent uniformly deconcentrated entries. I needed the assumption of ID rows, mean 0, variance 1. Then again, we have a completely tight behavior, small ball behavior of the smallest singular value of this rectangular matrix. So this question is for a matrix that looks like this. Maybe n is bigger than n, but we permit absolutely arbitrary n as long as n is bigger than or equal to little n. In some cases, I guess I'm soon going to be out of time. In some cases, one can improve these estimates. For instance, if your matrix is very tall and you know, your capital N is much, much larger than little n, then you need to assume much weaker. You need to place a much weaker assumption on the entries of the matrix to still have the sharp result. And furthermore, if you don't care about a very sharp probability estimate, you don't need to assume independent entries. You only need to assume independent rows and some anti-concentration property on the rows, and then you have the result